Good morning. I'm Dr. M. Fatima. Today I'm taking mechanical modeling of control system. The mechanical system, before moving to the modeling, first we know what elements are required in the mechanical system. The three basic mechanical elements are spring, damper, and mass. There are two types of mechanical system, translational and rotational. And the inputs given to these systems, force and motion, and which causes the elements to respond. Each of the element has one of the two possible energy behaviors. Either it stores all the energy supplied to it or dissipates all energy into it by some kind of frictional effect. So spring stores energy as potential energy, mass stores energy as kinetic energy, and damper dissipates the energy into heat. I'm taking a translational mechanical system. It consists of mass, spring, damper, or dashboard. The spring represent the stiffness of the system. Dashboard or damper represent the forces opposing the motion. The masses represent the inertia or the resistance to the acceleration. The mechanical system does not have to be really made of spring, dashboards, or masses, but have the properties of stiffness, damping, and inertia. So all these building blocks may be considered to have a force as an input and displacement as an output. In a linear mechanical system, the force is represented by F, velocity by V, displacement by X, mass by M, the coefficient of friction by B, spring constant by K. The mass is exhibiting the property that the bigger the mass, the greater the force required to give it a specific acceleration. So you can see this is a mass. If force is applied in this direction, then this mass will generate inertia force will be in opposite direction of this mass. So this force is actually equal to how much? Mass into acceleration. And acceleration is what? Rate of change of velocity with respect to time. So force is equal to m dv upon dt, where this velocity is the rate of change of displacement with respect to time. The displacement is denoted by x, so I can write here md square x upon dt square. So the force, inertia force generated by the mass is equal to md square x by dt square. Next is the damper element. This is an element which dissipates all the energy, and the force is proportional to the velocity. So the two So the force is proportional to the velocity for the damper element. If force is applied to the damper, then an opposite force will be generated by the damper, and this force is proportional to the velocity. If we remove the proportionality constant, then a proportionality constant is required to put up. So force is equal to B dx by dt. Dx by dt is representing the velocity. Next is a spring. If the force is applied, this spring will also produce an opposite force called a spring force. And this is directly proportional to the displacement. So to remove the proportionality, a proportionality constant can be added. This is represented by K. So the spring force is equal to K into X. Now let us we do one numerical. So let us we do a numerical. Write differential equation describing dynamics of system. This numerical is given, a mechanical system is given here. So let us we start. First of all, see two displacements are available here in the numerical x1 and x2. It means by applying force F1, the two displacements are there. And the system is having mass m1, damper, mass m2, and spring constant spring. So
For describing the dynamics of the system, it is required to make the free body diagram, equivalent diagram, and its equation. So first of all, I am taking free body diagram. Free body diagram is drawn for the mass. Let's first I take mass M1. So I'm considering here the force is applying in this direction on this mass M1. So this mass will generate a force opposite to the to this force. So this mass is generating inertia force. Let it be denoted by Fm1. Now see, this damper is also connected to this mass. So this will also generate an opposite force. So this, let this be represented by Fb. Now next, I am taking mass M2. Now this mass is connected to the damper beam. So a damping force is applying on this and providing a displacement of x2. So the force applying on mass M2, let this the direction of this force, let it be the direction. So this mass will generate an inertia force Fm2, and you can see here a spring is also connected here. So spring will also generate an opposite force. So let this be represented by Fk. So this is called the free body diagram. Okay. Now see, after making the free body diagram, uh, we can write the equations. So I'm writing the equation for mass M1. So you can see F is equal to Fm1 plus Fb. Let this be the equation number 1. Now I'm taking this equation. So the force which is applying in this direction, it is equal to the summation of these two forces according to D'Alembert's law. All the forces, the summation of all the forces is equal to 0. So see Fb minus Fm2 minus Fk. If I'm taking these forces here, like I'm writing here Fb minus Fm2 minus Fk. So this will be equal to 0. So see here the force Fb is applying here. So these two forces are generated in opposite of this force. So the minus sign is coming here. And the summation of these of all these forces is equal to 0. So this is the D'Alembert's law. Okay, according to this, this equation is also written. Now see the equivalent diagram for this. Uh, to start the equivalent diagram, we have to see how many displacements are present in the numerical. So x1 and x2, two displacements are available in the numerical. So I'm taking two nodes, x1 and x2. You know, make one base or ground or reference line. Now always remember the force is connected between node and ground, and mass is also connected between node and ground. So I'm writing here the force. I'm drawing here force between node and the ground. You can see here the force is connected. The force is connected on the uh, X1 node. That is what am I saying? That if force is applied, the displacement X1 will be available. So force is connected between node X1 and ground. Now connect the mass M1. Mass is also connected between node and ground. So see, M1 is connected at X1. So here one terminal of mass is connected to X1. Another terminal is connected to the ground. Similarly, mass M2 is required to connect. So see, mass M2 is connected. But where mass M2 is present? Mass M2 is present at node X2. So see, the one terminal of mass M2 is connected to X2 and another terminal is connected to the ground. Now see what uh, the element is connected between x1, x2, or between x1, x2 and ground. So see, this damper element is connected between two displacements, x1 and x2. That is between two nodes. So this damper is connected between x1 and x2 as shown in this diagram. Now see the only the spring is remain. Now see spring is connected at x2 and ground. So the spring is connected between x2 and ground. So now we know that the mass inertia force is equal to m d square x upon dt square, where x is representing the displacement. Now, since I'm writing the inertia force m1, so I'm writing at m1 here. So this m becomes m1. And now the m1 is connected to which node? It is connected to x1 node. So this is the x1. Similarly, if I'm writing the inertia force for mass m2, then what I have to write? Since mass m2 is present here, so I'm writing m2 here. Now mass m2 is connected to x2, so I'm writing here x2. Similarly, the K, the spring force is equal to Kx. Now see what is the value of spring constant here? This is K. So here also this is K. And it is connected to which node? This is connected to x2. So instead of writing x, I have to write x2 here. Similarly, the force, damping force Fb is equal to, this is equal to B dx upon dt. So see the B is connected here, and so I wrote here B, but the this B is connected between x1 and x2. So for by doing the nodal analysis, I have to write x1 minus x2 if current is flowing in this direction. So I'm writing here x1 minus x2 for x for the damping force. Since that this damper is connected between x1 and x2. Now, now see, now write the equations like we have already seen. F is equal to how much? F is equal to F m1 plus fb. So I'm writing here F equal to fm1. So I'm writing here m1 d square x1 upon dt square plus b dx1 minus x2 upon dt. So this is the equation number 3. Now take another equation fb equal to fm2 plus fk. So we know the value of fb, b dx1 minus x2 upon dt is equal to m2 dx2 d square x2 upon dt square plus the spring force is equal to k x2. So now this is the equation number 4. Now apply the Laplace transform to equation number 3 and 4. Now I'm writing here equation number 3. So f of s is equal to m1 for the Laplace of double differentiation, s square will come. And instead of writing x1, I'm writing here x1 as the initial conditions are taken 0. For the differentiation, s will come. Now apply the Laplace transform to equation number 4 as This is equal to M2. For the double differentiation Laplace, it is equal to S square x2 of S plus k x2 of S. So now this is the equation number 5 and equation number 6. So these two equations are describing the dynamics of the mechanical system. And you can see the mechanical system is written in the form of equations. So this is called the mechanical modeling. Now for this, the transfer function can also be calculated, that we will see in the next lecture. Thank you.